good afternoon, everybody, and also everybody through Zoom. My name is Daniel, and for this journal club session, I'm going to present a paper that I wrote during my master thesis entitled Attention-Based Regularization for Improved Generalisability in Medical Multicenter Data. So our approach was to try to have both a data-centric and a model-centric approaches to try to improve generalizability and evaluating it in a multi-center data scenario. So deep learning is an up-and-coming technology, and we are trying to implement models by feeding it extensive data sets and hopefully making the model to extract relevant information for a certain task that we want to solve. And in healthcare, that can happen because we have some databases that are excellent for deep learning, and then we can use these models to improve the healthcare situation, for example, by streamlining diagnosis or automating some boring routine tasks, and also promoting early disease prediction. And this can lead to more efficient treatment plans, and consequently, we can make, for example, less invasive surgeries or interventions to the patients, improving their quality of life, and also by reducing the hospital costs, general costs. However, doctors, as we all know, they have a high responsibility for their jobs, and they are normally facing some, they need to take decisions in some life-threatening situations. And in contrast, our AI models, they are not sentient until now, hopefully. So they lack any liability for the predictions that they make, and so they can make mistakes. But if a doctor is using an AI model, he is the sole accountant for the mistake. So we need to build some trust between the models that we create and the doctors. But we can ask ourselves, are our models trustworthy? So when we train in distribution data sets, they sometimes have good performance, but these models are normally super complex and they work in a black box system, so we don't really know how it got that prediction. Sometimes they can have some biases that we cannot detect, only later at later stages of the deployment, and also they can be quite data sensitive, and that's the topic that I'm going to focus on this article. So one example is that we can have some slight changes in the data distribution of the images, and this can lead to some prediction inconsistencies. So these slight changes are significant in medical imaging because if we think about it, we have several different hospitals with different scanners that come from different manufacturers. And then we have different technicians or radiologists assessing the image. So at the end, we have a lot of variability factors from X-ray to X-ray. And in some cases, for example, in these X-rays, we have a model that predicted negative for the lung collapse metastasis, and the radiologist that also predicted the same scenario. But using the same radiograph, but with different brightness and contrast settings, the model cannot, this change in the brightness and contrast may lead to a shift in the model's perception of the image, leading to a positive outcome, which is not what we want in the end. We also have a lot of publicly available X-ray data sets for the model training, and normally they follow some rules in order to make the data set ethical, private, and informative. However, there are some pre-processing steps that are not standardized, especially in X-ray. So we have several data sets with distinct imaging formats. For example, they can be stored in dichroms, so it's a lossless format where we have all the metadata information about the radiograph and also the raw image itself. But in other cases, we have just a picture, so a sampled version of the raw image. And these different formats hold different levels of information. And some sampled formats, they undergo image processing using the windowing levels. So the windowing levels, they are crucial to radiologists because it allows them to enhance some specific anatomical structures in the images. And they are comprised of two parameters, the window level and the window width. The window level is basically the pixel intensity midpoint of the radiograph. And if, for example, if we increase it, we will increase the overall brightness of the radiograph. The window width is the range of intensities. And for example, if we decrease it, the change from the dark to bright will be more abrupt. So in the end, these two parameters combined will determine the contrast and the brightness of the radiograph. And as we can see here, these are the difference between the original images and the sampled version of the same radiographs. And these changes may affect the model's robustness. And now in another different field, just to give you a bit of a broad perception of what attention is and what attention model is. So this simple example just tries to mimic what we want to do in deep learning. So for us humans, and especially for our eyes, for our visual system, our eyes capture the raw information about our surroundings, but we cannot process everything with the same quality level. So first we have just a specific area of that where we can really focus on a situation, and then we also have some choices that our brain makes of where to focus based, for example, on the colors, shapes, our mood, or if we have a certain task to perform or not. And researchers try to mimic this using the attention module. So first they used in the large language model. So the transformer is based on this attention. And I don't want to really explain what happens, but the key points is that we have these three different modules. So the query, the keys, and the values. The queries, we can think of it as an inquiry that we make, so a question that we ask. And then we have a dictionary with keys and values. And first we try to compare the query to the keys. So we build this attention map, so this relevance, we make a score of relevance of each key based on the query. And when we have this attention map, so the relevance score, we multiply with the value of the keys in order to have the self-attention feature maps in this case, because we are using self-attention, because the query comes from the input. So these self-attention feature maps are then added to the input. And in the end, we will have a new perspective of the input. So the input with highlights in some regions. So our strategy was to combine the data-centric of having different sampling scenarios, and also combine the model-centric approach of attention model combined with contrastive learning, in order to have a robust model where the disease information is somewhat disentangled from the X-ray characteristics. So to try to evaluate the generalizability, we built this multi-center scenario. So we would train, validate, and test the model in this dataset. It's a Brazilian dataset with the DICOM original images and also the PNG images sampled using the windowing levels. And to test it out of distribution, we would use the Shexpert, Mimic, and the VinDoctor. These are all chest X-ray datasets. And here are some examples of the images. So each row represents a different dataset, and we can already see here in the naked eye that there's some heterogeneity between the X-rays. So this looks promising, but we'll see if it works or not. So the first task, so we wanted to focus on the windowing settings. So what we thought of was just plotting these parameters and check if something would happen with the data. And it happened. So we could see the formation of these three different clusters. And by taking some random examples from each cluster, we could see significant differences in the contrast and the brightness of the images. So again, this is promising, but we wanted to really know if a model could try to take a grasp on these changes. So we just built a simple classifier for the clusters, for each cluster. And these are some representations of the GradCam on the top and the guided back propagation on the bottom. So I don't really want to focus where I don't want to know where it's focusing, but since we are talking about brightness and contrast, I just wanted a broad reception or activations, and also especially for the bottom. Okay, you can see uh, we can see some activation or higher activations in regions where we go from really dark areas to bright areas. So in some way, this is encoding the contrast as well. So we defined the first task, and the second one was so the disease classification. So the task that we wanted to remain invariant of the windowing settings. We chose atelectasis that corresponds to the partial or total collapse of the lung tissue, and this decision was made basically because we have this disease information across the 4 data sets that we were going to use, and it was the one with the most positive cases for training. However, we can see that there is still like a huge data unbalancement. For the baseline, we choose to have just a simple network based on the resonance encoding blocks. For our approach, we didn't want to change it that much in terms of the disease prediction. So we can see here that in terms of layers, we have 4 ResNet encoding blocks, and in our approach, we also have the same 4 encoding blocks. The only change would be that we would have a bifurcation at the top of the encoder, and in this bifurcation, we would be regularizing it by these convolutional self-attention maps. So we wanted to, as I told you before, in the perception, we wanted to have 2 different perspectives of the same input. And for the contrastive learning, we wanted to regularize these 2 attention maps by trying to separate them a bit. So we have, for each radiograph, we have both the original DICOM image and the sampled version using the windowing levels. And since it's the same radiograph, the disease information is the same. What changes is the brightness and the contrast. So by extracting the attention maps of each original and the sampled versions of the same radiograph, we will promote a similarity between the disease maps because they should be equal, and promote a dissimilarity between the windowing cluster maps in order to try to promote a disease variance to the brightness and the contrast. These are some implementation details, nothing too fancy. And here are the results. So we can see that our proposed approach outperforms the baseline in every evaluation, the in-distribution one and the out-of-distribution. And so we can conclude that this contrastive setting to the attention maps contributed to some of a disease invariance. So we can say that the disease prediction was a bit disentangled from the windowing settings, making a more robust model using the same data, basically. We also did an ablation study because we thought that maybe because we have pairs of the same radiograph, so we could just have data augmentation, and we saw that we couldn't outperform in the ablation for the Checkspert, but overall we still had huge gains of performance in the VIN doctor and also in the MIBIC dataset. So in conclusion, our proposal outperforms the baseline for the in and out-of-distribution testing, and we can say that these windowing settings are a source for variability, and also that we should use a bit more of the metadata information available in the datasets because they could help to build more robust models. For future work, we could try. So in this case, we only had one sample of each of a different brightness and contrast scenario for each radiograph, but we could generate all the 3 from all the 3 different clusters, increasing the size of the training data set, and also maybe trying to have an ordinal regularization. So the more different the contrast and the brightness settings are from the original one, the more similarity it should have. And also, we could try to experiment with other training data sets and also some other scanner features. For example, Mimic has a lot of features that could be used for sources of variability. And this is it. This was my presentation. And if you have any doubts or suggestions for the future work, I will be happy to hear. And if you don't, I will open the discussion of should we try to enforce disentanglement in these types of scenarios, or maybe try to build models that understand the entanglement between the two features. So yeah, thank you very much.